Good morning, class.
Good morning, Dr. Miller.
Yes, you may be seated. You may be seated. So, today we will be going over how to find the average potential over a spherical surface. So, if we are given a spherical surface with a radius, so radius of big R, and a point charge Q. Point charge Q. Okay. And it's located on the inside of the spherical surface. So what we want to do for this example is we want to show that the average potential is equal to the potential at the center of the sphere plus the Q enclosed over 4 pi epsilon sub naught big R, where V center is obviously the potential at the center due to all of the external charges, and Q enclosed is obviously the charge on the inside of the sphere. So, we want to find that. There we go. So this is what we're given. Okay, so the potential at a point on the surface of a sphere is given, or we learned in another class, so it is given by V is equal to 1 over 4 pi epsilon sub naught Q over R. Now, so first we need to calculate the average potential over a spherical surface of radius R inside, or due to a single point charge Q located inside of the sphere. Okay, so what we're going to do is we're going to imagine a point imagine a point at Z is greater than R. Okay? So, at this point, we would find that this R here, so we would find that, let's say at Z is less than R, we would find that R squared is equal to Z squared plus big R squared minus 2RZ cosine theta. So, from there, we also know that, so V average is going to equal 1 over 4 pi big R squared times Q over 4 pi epsilon sub naught and this is where it gets tricky. So then it's times the integral of Z squared plus R squared minus 2RZ cosine theta from Z cosine theta to the negative 1/2 R squared sine theta d theta d phi. So then, when you solve this, it comes out right here as, this comes out to be Q over 4 pi epsilon sub naught times 1 over 2Z big R, and then when you integrate, you get square root of Z squared plus R squared minus 2 big R z cosine theta from 0 to pi. Okay? So now, because you know that because of the range of d phi, so when you integrate phi, its bounds are always from 0 to pi. So, now taking this one step further, you end up with q over 4 pi epsilon sub naught times 1 over 2 z big R times z plus R minus z. And now all of this simplifies down to 1 over 4 pi epsilon q over big R. So, now you can imagine in a charge-free region where the Laplace equation is valid, the value of potential at point R is going to be equal to the average potential over any spherical surface centered on R. So what I'm saying right here is that the V center equals V average. Now, if there is more than one charge inside the sphere, the average potential due to the charges inside, so the potential at the center is equal to the average potential. Now, if there's more than one charge inside, the average potential is going to be equal to, if more than one charge, if NQ is greater than 1 inside, V average is equal to 1 over 4 pi epsilon sub naught Q enclosed over R. Now, the potential due to all external charges is the same thing as V center. So, the net potential over a spherical surface is equal to V average equals V center plus 1 over 4 pi epsilon sub naught Q enclosed over R. And this concludes our video. This was proving that the average potential over a spherical surface is equal to the potential at the center of the sphere plus the Q enclosed over 4 pi epsilon sub naught